The best way to picture an atom is as a compact, dense nucleus encircled by buzzing.
Test 1, 2, 3. Percubaan mic 1, 2, 3. Ladies and gentlemen, announcing the arrival of the chairperson, Majlis Professor University, as official representative of the UTHM Vice Chancellor, the speaker for Syarahan Perdana Series 3 2024, and the Dean of Faculty Applied Science and Technology UTHM. Ladies and gentlemen, please stand up. Lagu Bangsa Johor and Negaraku. Ladies and gentlemen, please be seated. Ladies and gentlemen, to start this event, we would like to invite Ustaz Muhammad Syarif bin Abdul Muttalib of Islamic Center UTHM to lead the recitation of Dua. Please welcome.
Assalamualaikum warahmatullahi wabarakatuh. Nabiul Karim Mustafa Rasulullah sallallahu alaihi wasallam. Al-Fatihah. A'udzu billahi minasy syaithanir rajim. Bismillahirrahmanirrahim. Alhamdulillahi rabbil alamin. Ar-Rahmanir Rahim. Maliki yaumiddin. Iyyaka na'budu wa iyyaka nasta'in. Ihdinas siratal mustaqim. Siratal ladzina an'amta 'alaihim ghairil maghdubi 'alaihim waladdallin. Bismillahirrahmanirrahim. Alhamdulillahi rabbil alamin. Wassalatu wassalamu ala asyrafil anbiya'i wal mursalin wa ala alihi wa ashabihi ajma'in. Allahumma ya Allah, dengan hati yang penuh khusyuk dan tawadhu', kami bersyukur kepadamu kerana dengan keizinan dan kurniaan-Mu, maka dapatlah kami berhimpun pada pagi yang mulia ini, bersempena dengan Majlis Syarahan Perdana Siri 3 2024. Semoga majlis ini memperoleh hamparan ilmu dan petunjuk, keredaan dan taufik, serta keberkatan daripada-Mu jua ya Allah. Allahumma ya akramal akramin, ya Allah, berikanlah kepada kami ilmu yang bermanfaat, keselamatan dan perlindungan kepada kami juga keselamatan buat seluruh kaum muslimin dan juga keluarga kami. Jauhkanlah kami dari perasaan resah gelisah, gangguan kesihatan dan tidak fokus terhadap kerjaya kami dan tidak selesa. Kukuhkanlah keimanan dan keyakinan kami, serta peliharalah kami dengan dipermudahkan segala urusan pekerjaan dan hidup kami, serta keselamatan zahir dan batin. Ya Allah, ya Tuhan, ampunkanlah dosa-dosa kami, dosa kedua ibu bapa kami, pasangan hidup kami, anak-anak kami, kaum keluarga kami, guru-guru kami, sahabat-sahabat kami, serta sekalian muslimin mukminat, muslimin muslimat, mukminin dan mukminat di mana sahaja mereka berada, sama ada yang masih hidup ataupun yang telah meninggal dunia. Allahumma ya Hannan ya Mannan ya Badi'as samawati wal ard ya Dzal Jalali wal Ikram. Kami juga memohon dengan keberkatan majlis ini, Kau peliharalah kami dari segala mara bahaya, penyakit dan perasaan duka cita. Terimalah segala amal saleh yang kami lakukan dan ampunkanlah dosa-dosa kami di dunia dan di akhirat. Rabbana zalamna anfusana wa illam taghfir lana wa tarhamna lanakunanna minal khasirin. Rabbana atina fid dunya hasanah wa fil akhirati hasanatan wa qina adzaban nar. Wa sallallahu ala sayyidina Muhammad wa ala alihi wa sahbihi wa sallam. Walhamdulillahi rabbil alamin. Qabbalallahu.
Amin, amin ya rabbal alamin. Thank you, Ustaz. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And a very good morning. The Honorable Professor Technologist Dr. Hajah Roziati binti Ibrahim, Chairperson of Majlis Professor University, as official representative of the UTHM Vice Chancellor. The Honorable Professor Technologist Dr. Rabiah binti Ahmad, Deputy Vice Chancellor, Research and Innovation. The Honorable Professor Technologist Dr. Zaidi bin Embong, Faculty of Applied Science and Technology, UTHM. The Honorable Wan Zahra bin Abdul Samad, Head of Library Perpustakaan Tunku Tuan Aminah, UTHM. The Honorable Associate Professor Dr. Muhammad Zaki bin Noh, Dean, Faculty of Applied Science and Technology, UTHM. Distinguished guests from institutions and industries, members of Majlis Professor University, senior officers, academicians, students, ladies and gentlemen. Welcome to the third series of Syarahan Perdana 2024. Alhamdulillah, all praise and thanks to Allah Subhanahu wa Ta'ala. With His guidance and blessings, we are here at the big stage Perpustakaan Tunku Tuan Aminah UTHM once again for the third series of Syarahan Perdana 2024 by one of the members of Majlis Professor University UTHM. Ladies and gentlemen, without further ado, we would like to invite the Honorable Associate Professor Dr. Muhammad Zaki bin Noh, Dean Faculty of Applied Science and Technology, to introduce and later will invite our honorable speaker for today, Professor Technologist Dr. Zaidi bin Embong, to deliver his lecture. Please welcome.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Dan selamat pagi. The Honorable Professor Technologist Dr. Hajah Roziati binti Ibrahim, Official Representative of the Vice Chancellor. The Honorable Professor The Honorable Professor Dr. Rabiah binti Ahmad, Deputy Vice Chancellor, Research and Innovation. The Honorable Puan Zahra binti Abdul Samad, Head of Librarian, Perpustakaan Tunku, Tun Aminah UTHM. The Honorable Professor Technologist, Dr. Zaidi bin Embong, Faculty of Applied Sciences and Technology, UTHM. Distinguished guests from industries, members of Majlis Professor University, senior officer, academicians, students, ladies and gentlemen. I'm honored to introduce our speaker today for this event. Bismillahirrahmanirrahim. Technologist Dr. Zaidi Embong attended Malacca High School before pursuing an undergraduate degree at University Technology Malaysia, UTM, from 1991 and 1996. After completing a science and science computer education degree, he progressed to the next level and received an MSc in physics from the same university in 1998. In 2023, he went to University of Bristol in England to pursue PhD studies under the supervision of Professor G.C. Allen, a well-known surface science expert. His PhD was awarded in 2008 for a spectroscopic study of uranium oxidation and its alloy, U6% niobium, utilizing an advanced surface analytical technique known as X-ray photoelectron spectroscopy, XPS. He joined UTHM in 1999 and has been an academic there for about 25 years. His professional experience has also been beneficial in assisting the Faculty of Applied Science and Technology, FAST, UTHM, particularly in teaching, learning, consulting, and mentoring research. He is a professor in physics at the Faculty of Applied Science and Technology, FAST, UTHM. He was appointed principal researcher at the Research Center for Soft Soil Research, Integrated Institute of Engineering, I2E, UTHM. His research interests are diverse, including surface science, vacuum physics and thin film, metal alloy corrosion, nuclear physics, radioactivity monitoring and evaluation, and environmental physics, soil and water remediation. He also specialized in spectroscopy research, particularly sophisticated surface examination technique, including X-ray photoelectron spectroscopy, XPS, OJ electron spectroscopy, AES, and laser Raman spectroscopy. Between 2008 and 2016, Dr. Zaidi served as the UTHM Journal of Science and Technology editor. As a scientist researcher, he has published over 100 manuscripts in the Scopus and WOS Index. He has 15 years of experience working as the international peer reviewer for various high-impact journals, namely the Journals of Alloy and Compound, Elsevier, Applied Surface Science, Elsevier, Chemosphere, Elsevier, Environmental Pollution, Elsevier, Journal of Environmental Chemical Engineering, Elsevier, Materials, Chemistry and Physics, Elsevier, Materials and Design, Elsevier, Microchemical Journals, Elsevier, Physics and Chemistry of the Earth, Elsevier, Surfaces and Interfaces, Elsevier, and Materials Today, Elsevier. Besides, he also contributes as a reviewer for several other high-impact journals, such as the International Journals of Environmental Analytical Chemistry, Taylor and Francis, and Journal of Springer Nature. In 2017, he was awarded 2 prestigious Elsevier Awards, Outstanding Contribution in Reviewing for the Journals of Alloy and Compounds, and Applied Surface Sciences. As principal investigator and co-investigator, he has secured a grant from internal and external sources amounting to Rm 988,340. Aside from that, he is also responsible for consulting with national agencies. He has served as assessor and interviewer panel for several activities with the Ministry of Higher Education, KPT, including interviewing for 2 KPT scholarships, My Brains and Malaysian International Scholarship, MIS, and evaluating Fundamental Research Grant, FRGS, of Applied Science and Technology Cluster. His disability as a result of muscular dystrophy disease after returning from England has made him one of the Malaysian disabled scientists. He received the National Level Award, Special Award for Disabled Academician from the Malaysia Social Welfare Department in 2018 in recognition of his excellent contribution to the academic field. As a scientist in a wheelchair, he has given back to the community at the state level by serving as the advisor for the Malacca Deaf Sport Association, MASDEF. In 2019, he was invited as an invited speaker for sambutan Hari Orang Kurang Upaya OKU and Warga Emas Johor to inspire Johor's disabled community to pursue higher education. Last but not least, he was the recipient of the National Workers Icon Award, OKU, during the National Labour Days 2024, which was presented by Yang Amat Berhormat Datuk Seri Anwar Ibrahim, the Prime Minister of Malaysia recently, PMX. Sekian, wabillahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh.
Bismillahirrahmanirrahim. Yang saya hormati Profesor T.S. Dr. Hajar Roziati binti Ibrahim, Wakil Rasmi Naib Chancellor merangkap pengerusi Majlis Profesor UTHM. Yang berbahagia Profesor T.S. Dr. Rabia binti Ahmad, Timbalan Naib Chancellor Pendidikan dan Inovasi. Yang berbahagia Puan Zahara Tiada Samad, Ketua Pustakaan UTHM. Yang saya hormati Profesor Madya Dr. Muhammad Zaki bin Noh, Dekan Fakulti Sains Penggunaan dan Teknologi. Pegawai-pegawai kanan universiti, wakil-wakil industri serta wakil-wakil daripada KPT, daripada IPTA. Saya nampak tadi ada sahabat-sahabat saya dipahamkan ada wakil daripada MIMOS, daripada ST Microelectronic MUA serta wakil daripada UKM. Prof Azman Jala dan juga Prof Insan, terima kasih. Thank you for coming. Okay. Dan juga sahabat saya Dr. Azli daripada UTM. Terima kasih datang. Okay. Kemudian ahli-ahli majlis profesor UTHM, pegawai-pegawai universiti, para pensyarah, para pelajar saya sekalian, dan seterusnya para hadirin sekalian. Okay, sebelum saya mulakan syarahan saya, izinkan saya untuk meletakkan handphone ni dulu. Okay. Jadi saya ingin ucapkan terima kasih kepada majlis profesor dan juga fakulti kerana memberi saya untuk berada di atas pentas yang amat besar ini. Okay. Dan berlatar belakangkan skrin yang besar. Okay. Jadi saya rasa ini adalah suatu penghormatan. Mungkin sekali seumur hidup saya berada di sini. Dan juga mungkin pada 13 Mei mungkin sejarah tercatat profesor yang pertama berada di atas kursi roda yang berada di atas pentas ni. Okay. Jadi kalau tengok cerita X-Men tu dia ada watak Profesor X kan. Okay, itu Profesor X yang ni fantasi ni yang betul-betul. Okay. Alright. So sebelum saya mulakan syarahan, izinkan saya untuk menyampaikan syarahan dalam dua bahasa. Okay. Alright. Okay. The topics that I'm going to share with all of you is regarding to the ESCA that I will let you know later on, ESCA, and then we use it to probing, or to investigate the advanced material surface. Okay, right. So I will discuss in detail later on. But before I go ahead with it, allow me to tell you a story about myself, because some of you maybe know me just on my WeChat, but you don't know the story. What is story all about? Behind it. Okay, right. So I will start with this. All right. So maybe some of us confused about my research area, because yes, I have been as a principal researcher at research. Thank you to Prof Adnan to accept me as a member of research. But actually, my research area is very diverse. It's not focused on only one area. So it's look on this, right? The story is here. Why is the reason why I have to become a multidisciplinary scientist? Because of, you look on the title of my thesis, starting from my degree, first degree, So my first degree from UTM Skudai in 1996. So my thesis, my bachelor thesis is something about, if you look at read that one, the taburan kepekatan uranium and thorium serta aras keradioaktifan alfa dan beta di dalam sampel tanah di daerah Pontian. Okay, and then in 1998, I continue my master at the same institute at UTM Skudai. So my research is much focused on the application of X-ray, by the way. So you look at the title, teknik analisis unsur suri di dalam sampel sedimen dengan menggunakan spektrometer pendaflow sinar X sebaran tenaga bersasaran sekunder. So during that time, I think Prof Zaki, we are in the same laboratory. He know me very well, actually. We are working in the same laboratory. My dean, Dr. Zaki, we have work together, right? Yeah, I think you remember the nostalgia, very nostalgic, right? And then in 1999, and then after that, 1999, I joined UTHM. During that time, it's not UTHM, it's known as ITTHO, Institute Technology Tunisia On. So I joined in somewhere around in middle of June 1999. And afterwards, I married with my wife, Dr. Salawati. Is there? Okay. And after that, 3 years after that, we go to UK to pursue our study. Right, and my PhD is respect to title under spectroscopic study of oxidation of uranium and its alloy. Now, from all these 3 theses, I put the keyword over there. You can see the keyword is the keyword of my expertise is surface sign, and then we have X-ray analysis, metal and alloy, radioactivity, salt and sediment. So I put all the things together. So I can become anywhere then, because I can be material scientist, I can become, nuclear scientist and so on. Okay, right. Okay, that's a story. So I hope after this, nobody asking me why I was in research. Yeah, even I can join anywhere, by the way. Okay, I think Prof. Perdana will, the first person will stop me from go away from other COE. Prof. Nan, yeah, just joking, Prof. Nan, yeah. Right, then this, very nostalgic picture I've shared all of you. So this photo during my master, awarded by Sultanah Ajanaria, UTM, and then this is my thesis, yeah, and this is my PhD scroll. Okay. Right. Okay. Now about myself a bit. I start my bachelor in UTM Skudai. And you see there's my photo with my late father, Allahyarham Embong bin Mahmud. So before I proceed my lecture, please recite together Al-Fatihah to my late father, Embong bin Mahmud. Bismillahirrahmanirrahim. Al-Fatihah. Al-Fatihah. Okay, there's my late father. One sad story I need to tell already. Yeah, my late father passed away during I am in UK. I'm not around. So when after return, the grave had been covered by the grass, and then after 2 years, and I have a chance to visit my late father's grave. Yeah, so it's all about sacrifice of knowledge. Yeah, right. And also that's me in front of UTHM logo, and then that is my apparatus in UTM. You see the pinjana sini they call X-ray generator. So behind that is my system. You can see the silicon lithium detector. You got the nitrogen. We use the cryogenic system over there. And behind me there is an X-ray system. I think Prozaki remember the system. SRD, Prozaki, yeah. And then with my wife during this time we are engaged, not married yet. I still remember. Yeah. And then you can see the next photo. That's my photo behind. At Ashway Building Physics Laboratory at University of Bristol. And next we have a photo of my Professor G.C. Allen. He's an expert in surface physics. And then with my colleague, this is during my viva. Yeah, a photo during my viva. And this is the day I submit my thesis and the time for me to return home. And finally, happy ending with my family. And my wife, after several years, she managed to get her PhD. Okay, that's my story. And about my experience in UK, yeah, I can share with you my experience, because some of you don't have a chance. So let me share some story. That is with my friend, Mr. Jonathan Hawking. He's the first person. He's a technician, by the way. The technician in UK are very expert, They are expert. So I learned from him. Okay. So you got a lot of things behind me. That's a very complicated machine. And with my wife, my first daughter born in UK, Adlina Zawani. She's there, Adlina. Yeah. Okay. And then with my colleague. And for information, during I studied in ISC, I'm the only person from Malaysia. Only me. Even the Mat Saleh thought I am Latin. Yeah, that's true. If you go to UK, some Latin, like from Venezuela, Bolivia, or Brazil, they're skin like us. Yes. And then, and as I am the only Malaysian, and I think I am the first and the last student of Professor G.C. Allen who from Malaysia. And Professor G. Shailen had been in Singapore long time ago. He's appointed as a visiting professor. And yeah, to me, I feel very proud to be his student then, okay? Because thing is, it's not easy, you have to get supervision under very famous supervisor, yeah? So with my friend, Dr. Richard Ball, now is in Bath. We have, this is, I still remember his name, yeah? Graham, okay. He's from Oxford now. And then Dr. Adi Al-Turki is from Libya, but he's working in my lab, right? There's Dr. Keith Allen, and then our late Professor Ron Stephen from Bath, and then there's my professor, yeah. Right, this is the environment, working environment over here. We have Marco, my friend from Italy, Dr. Christopher from UK, yeah. And no wonder until now everybody noticed that I love to selfie. Even now, I think I want to get my grab on my phone to selfie all of you. Because you can see my habit like that. Long time ago, I'm not only selfie with people, but I also selfie with a machine. During this time, I use a very bulky phone. I call it Nokia Karipap. During that time, there is no selfie mode. What I did, I turn it over, and then I smile, and then take a photo. And then I think this photo will be useful in the future. That's true. Now you can see me in front of my machine there. You see, very complicated. So, student, you can do this afterward. Keep it as memories afterward in your lifetime. Yeah, you know, in Pago we got a lot of things, a lot of equipment. Go and selfie. Okay? All right. Now behind me got a lot of systems. See, there's my system, and this is how the system look like, and then that's me. Yeah, so my face is totally different, not like now, you see, much different. And you see, very crowded system, okay? Right, I will explain in detail later on. Okay, here with my Professor G. Allen, as I said, he's a physics expert, and with Julie Gray, he's a secretary of Jeff. Every single time I have to submit a report to Malaysian government, of course, I need to deal with her then, okay? And then with my, I treat him as my dad as well. This is Dr. Charles Yones. Yeah, he's very close to me. He is the one who helping me in doing the analysis. Oh, yes. And this is the turning point of my life. Yeah, so this is the turning point of my life. And for your information, the first time I go to UK, I have already suffered this disease. But in my heart, I think I have to go ahead to go higher. It's we call fisabilillah. We sacrifice for good thing. And the story happened here with my wife there. The doctor, the nurse have been diagnosed me, and then I think they expect from Poland. He say, Zaidi, I think another 5 years time you end up your life on the wheelchair. And then during that time I not believe it. But I accept it finally. And yes, that's true. And then my muscle is keep on, weak progressively until now. Yeah. So just what I did is pray to Allah. Yeah. All right. That's happened. And then at Frontier Hospital, the same hospital that our late Professor Stephen Hawking do. Our late Professor Stephen Hawking also have a treatment at the same hospital. He lives somewhere around, I think, in Oxford. And I've been there before. So that's why I took a photo. Even we are the same position as a professor of physics. He's from, but UK, I'm from Malaysia. Okay, right. Next. Right, there's, after struggling, and finally I go to submit my thesis. And then this is a final photo. This is the desk that I managed to secure my Viva. Very simple one. It's in the lab, not in special room. In my lab, the place that I do my job, that's the place I pass my Viva, And then with my good friend, this is my best friend, my colleague, my lab colleague. Now it's not professor now, Professor Tom Scott. I think Prof Hashim, no, Professor Tom Scott. Yeah, okay. Right, Professor Tom, very tall guy. Every single time I have to speak, I do like that. Very tall guy. And then with my Malaysian friend, Mr. Zol, Mr. Wan there. And then this is the day I submit my thesis. You see, every single thing I record. That is my habit. But finally I can show you my story. Now you can believe it, right? I'm not joking. The last time, and then finally my thesis have been in the chef of British Library, yeah? So we submitted to British Library. And yeah, this is the last day, the Malaysian committee, not so many. The first time I get to UK, about 7 family, not so many. It's not like Manchester, not like Birmingham, yeah? Okay? Right, bro? Okay. And then, that is the end of my journey, by the way. Now we talk about something deal with my career in UTHM. Yeah, that's me. Very tough, handsome guy. Right, that's me, yeah, long time ago, 1999, you see? It's somewhere around C08. This is my first room. And during this time, Prof Hashim is my head department. Prof, thank you for coming, Prof. And then there's my wife. This is our old convocation gown with my wife. And then I stand in front of our Kuito. Yeah, the same gate, but with different name. From Quito to UTHM. And also, that is a photo of my tag name, starting from lecturer, DS45, and then pensyarah kanan, DS52, and then as an associate professor, DS54, and finally, now, Alhamdulillah. Yeah? Okay. Right, so that's me. And then, during the induction, this is my induction. Yeah, in order to confirmation, of course, every single staff had to perform the induction. So canoeing at somewhere around the Sungai Endau Rompin, yeah, with my wife, and I am the head of the Boria. Prof, I think, which guy, all the staff, yeah, I'm a leader of the Boria during the time. And then, yeah, with our Professor, our former Vice Chancellor, yang berbahagia, Professor Datuk Ismail Bakar. He's a top man at recess. He's the first person who established recess. And I think Prof Adnan know very well Datuk. Yeah, we already always invite Datuk to come over to visit our research center. And this is the first module during 1999. I think Prof Zaki remember this. Now, during that time, hard copy. Now all notes are in PowerPoint. Students just ask the lecturer, note straight away. But yeah, we print it. Yeah, no issue. And this is my working environment. I'm very happy with my student. Yeah, because the student make me very happy. Yeah, sometimes even I keep on shouting at them in the class, but after the class, I can happy, and so on. Can keep on smiling. Okay. This is the first batch. Kim. I don't know what happened. Okay. Sorry, coincidentally I pushed the button. All right. So this is the first batch. My student, until now, Kimi is there. Kawarismi, where's Kawarismi? Is my PhD student now. Starting from bachelor, master, PhD. The same under the same supervision. Congratulations. And also Shapika, yeah, under my supervision as well. Yeah? And then with my student, you can see keep on happy with my student. This is serving at the Campus Pago, yeah, deliver the lecture to the student. And then this is one of our OKU student. My task is we are in the same position. I keep on, always talk with him to encourage him, yeah, to pursue study. This is how it look like, yeah. Right, and then with this is my postgraduate student, yeah. I have a student, Mona, and then we have Patama, she's from Muscat, Oman. And then with Mariam, she's from Dubai, UAE. And then, we have Shapika. Shapika is there? Yeah, Shapika. Yeah, she's my PhD student now. And some of students, and also we have Dr. Sapuan. I think Prof Hashim, Prof Zaki remember this, our staff now is already, yeah. Right, and also this is during Convocation Day for the student to celebrate all of them with staff, research staff, Prof Adnan. Yeah, Prof Adnan is here, yeah, research. Yeah, thank you to research, by the way, to having me as their principal researcher. Thank you, Prof Adnan, yeah, okay. Yeah, now we see with my Prof Adnan, this is how I work in the lab. Prof Adnan keep on supporting me. Yeah, and also I have set up one what you call Python remediation reactor long time ago under using a grant, yeah, research grant from FRGS, something like that. Okay, right. This is how we do the free work. You can see Prof Adnan also always will be with me. He keep on supporting me. Thank you, Prof. Again, Prof. Yeah. And before I start with my lecture, of course, because I love photo, selfie, I got a lot of photo. Prof. Hashim, my mentor, Prof. Thank you, Prof. Since 1999, Prof. Until I become professor, Prof. Thank you very much. I owe you so much, Prof. Thank you. Yeah. And then with Prof. Datuk Ismail Bakar, with our former Vice Chancellor, we have Datuk Nur Dalimin, Datuk Wahid Razali, and also now our present Vice Chancellor, Prof. Datuk Ruzairi. Okay? All right, that's my story. Now we go ahead with the lecture now. Okay? All right, so the topics is cover all these topics. So in this lecture, I'm going to explain to you, the first one maybe regarding to the concept of the surface time. And then afterward, we go ahead with the concept of vacuum physics. And then later, I'm going to touch on the SPS, and last one, but not least, going to the application. Right, now, before we start, I think it's good for us to, we start from this kind of analogy. Either you are realized or not, every day we are surrounded by a surface and layer. Very simple example is our face. Our face is a surface. The interface also in our life as well. Everywhere we go, we have interface. Why? We are working, we are moving from one point to one point, and in the atmospheric environment. So our body always exposed with air. So there is interface between the skin together with the air. That is interface, right? So, and why? Why I give this kind of analogy? Right, when we talk about the Earth is consists of several layers. The layer that we can see is starting from, because if you look at on the Al-Quran, even Al-Quran also tell about the Big Bang as well. How the formation of the Earth is starting from the inner side to outer side, actually. And from the Big Bang. That if you look at on this, starting from the core, and then we have outer core, mantle solid, and layer layer, and then we are somewhere on the top layer of the Earth. Yeah? Right. Now, why I give you this kind of idea? Because I think this is very important. But this is in large scale of layer. Large scale of layer. But later I will explain to you to smaller scale of layer. Now, on the surface of Earth, normally, there are abundance of metal. Abundance of metal. We got a lot of kind of metal. Now, if you look at on the periodic table, all the element of metal is come from the Earth by extracting the mineral to become we call the metal. Yeah. So you look at on the periodic table of element, you got lots. In 1869, Dmitry Mendeleev has sought out all these kind of element. And to me, when you talk about metal, it's not the metal that exists, that we see around us, is not pure solid. It's not pure solid. Why I say that? The reason is because there is a formation of oxide. Except if you ask our astronaut, Datuk Syekh Muzaffar, to bring that metal to the outer space, then I can believe that is pure metal. You polish it, and then the metal can be very clean. That's why Some metal are very expensive. Now the price of gold are rapidly increased now, right? Gold are expensive. Platinum are very expensive. What makes this kind of gold and platinum is very expensive? Anybody can answer me why? Okay, the reason is because it is innate. Innate, so special. Yeah, it's so special. It's very hard to form the oxide on that kind of metal. It's not easy. All right, because of this, since my lecture are regarding to a metal, regarding to a surface, and also regarding to interface, I think it's good for me to quote, because to me I believe that the science is always come from Al-Quran. The science is always come from Al-Quran. Yeah? All right, so allow me to read several surah. Yeah? If I'm wrong, please Ustad can help me later how to, yeah? All right, so we start with the first surah, Surah Al-Hadid. It says, A'udzubillahi minasyaitonir rajim. Bismillahirrahmanirrahim. Laqad arsalna rusulana bil bayyinati wa anzalna ma'ahumul kitaba wal mizana liyaquman nasu bil qist. وأنزلنا الحديد فيه بأس شديد ومنافع للناس وليعلم الله من ينصره ورسله بالغيب إن الله قوي عزيز. The words, if you look at on the translation, the word hadid is metal. So Allah sent the metal from the heaven to the earth for the benefit of the humankind. But in the Quran say, metal is not classified copper, zinc, aluminium, and etc. That's why in Al-Quran, already say, for those who are think. The Quran encourages us to think, to investigate, to find, to solve it. Right. Now this is the first surah that relates to metal. The next surah is related to concept of layer. To me, I believe this is a concept of layer. Bismillahirrahmanirrahim. Allahu allazi khalaqa sab'a samawati wa minal ardi mislahunna yatanazzalul amru bainahunna lita'lamun anna Allah ala kulli shay'in qadir wa anna Allah qad ahata bi kulli shay'in ilma. So over here it says Allah form 7 layers of heaven, 7 layers of earth, but it's very long scale, big scale, 7 layers. So meaning now, that's why I say every around us we have a layer. And last surah that I try to quote, that's to interface. The concept of interface in from Surah Al-Furqan say, Bismillahirrahmanirrahim, وهو الذي مرج البحرين هذا عذب فرات وهذا ملح أجاج وجعل بينهما برزخا وهجرا محجورا. So in this concept, Allah tells us 2 kinds of different water are split by membrane. One is bitter, one is plain or salty. The membrane are very small. That is a concept of what we call interface. Yeah? All right, now we proceed. Right, what is the surface? The surface, from the dictionary, say, surface can be 2-dimensional boundary of the material body having 0 constant or very curvature. So it means that the surface can be smooth or not smooth, like us. Some people, their face very clean. Some people, their face have a pimple. Something like that. Am I right, Prof? Yeah. So, yeah. Clean, very handsome, right? But I got pimple then. Okay, but the thing now, I say, there are varieties of, this is in 2D. Yeah? So talking about the surface. The surface we are talking about is at the uppermost layer. Uppermost layer over here. Yeah? So this is a concept of surface. The surface is 2D. Next, we have the next one, what we call as interface. Interface is defined as the boundary between 2 spatial regions occupied by different matter. So when we talk about matter in science, we have three kinds of matter. We have a solid, we have a liquid, and we have a gas. And there is another fourth matter, what we call a plasma. A plasma is only exists at the surface of the sun, for example. At high temperature of degree, there is a plasma. But in general, we consider there are three matter. So we look at over here, the concept of surface. Now, from this photo, you can see, for example, the interface between solid and liquid over there, and also the interface between liquid and gases. It's not only gases, but also with the vacuum, if the sample are in the vacuum region. All right? So this is the concept of interface. Now, all of it, from the concept of surface, the concept of interface, then we have surface science. So what is surface science? Surface science is the study of physical and chemical phenomena that occur at the interface of two phases, including solid-liquid interface, solid-gas interface, solid vacuum interface, and last one but not least, liquid gases interface. So, right, so from here, what we have a two term. We call as surface chemistry and surface physics. Okay, whereby the surface chemistry is the study that focus on chemical reaction that occur at the interface or the surface. While for the surface physics, we will focus on study of physical change that occur at the interface. There are two different regions there. Yeah, so chemical is more toward what we call two term here, very important, which is the origin of the formation of sites come from these two process we call as chemisorption and persorption. All right? Now these two things. Right, next we have now why is it all the metal are not pure? Because of this reason. Yeah, so I hope after this all students remember the metal is not pure. Actually, yeah, it's covered by coating. Right? Now, why I say that? Because every single material surface on the earth will react with the gases at the atmosphere. So in our atmosphere, we have about 70% of nitrogen, 31% of oxygen, and the rest with trace amount of gases. So this kind of gases will interact with the surface. Why? Why the gases can interact with the surface? The reason is because there is a surface energy. Let's make the material like magnesium, for example. Yeah, for example, very simple example, you take Panadol, soluble, and then you immerse it in the water. What happens? It will be bubbling. Very react, all right? So same to like metal like magnesium, yeah, natrium, so on. So the surface concept here, the surface energy, that lead to the formation of what we call as native oxide layer of material surface. So in this context, the formation, right, sometimes it gives advantages, sometimes it's not. Advantages like it will improve the property of the material. Advantages that it will be degrade the material surface. Now, for example, yeah, we have a titanium over here. So normally what you have, titanium starting from the metal sulfate, and then one after this titanium, yeah, react with the gases, we form the first layer of TiO. And then after continue with Ti2O3. And the final one is TiO2. Same to the others. That's why in terms of ferrum, for example, that's why some of ferrum you add, especially nearby the sea or ocean or beach, yeah, the metal become corroded. Why? Because it's very close to the salty environment. Very salty environment. I think Prof. Insan, we have Prof. Insan, he explained in corrosion. I learned a lot from him. We have Prof. Insan from FST. You can give a clap to Prof. Insan. Prof. Insan, thank you. Yeah. All right. Thank you, Prof, for coming, Prof. Yeah. Okay. Right. So you see, this is the layer. Whereby this is steel, and then we have the oxide layer, and so on and so on. That's why this make the layer become multi. There's only not one single species. They got multi species all layer. Right, I have about nearly 200. I try my best to finish out, yeah? All right. Now, talking about the surface energy, Why the material have a safe energy? The reason is because of, if you can see, for the atom that in the intensity side, that in the bulk of the sample, you can see all the atom are close to each other. There is formation of intermolecular bonding, whereby the atom in the middle here will be bond with the neighbors atom. While for the top one here, you can see, got four bonding formation there, not 6. And the other 2, this we call excessive energy. Excessive energy. This excessive energy, this is the energy that allow the surface to be react with the gases or maybe water vapor. That's why we have the concept of surface tension. And that's why we have contact angle. Contact angle. I believe that there is contact angle machine. I think Prof. Fiona Soon. PM Fiona Soon. Contact angle. Please respect to this one. Okay. Right, next one. Talking about the ration, you got law of ration. You have a surface division, we have separation, we have and so sometimes the gas is not sticking on the metal, but it's sometimes because thermodynamically, so it will release, it break the bonding and release for example, H2O. H2O we break out and then we release hydrogen to the environment. So that we call desorption. We have the 2 phenomena, absorption and desorption, okay, on the metal surface. Now the formation, when we talk about the formation, I thought some of us are very familiar what we call as assembly, self-assembly. Right, Pro Cairo? Self-assembly, right? So, how the formation of the surface occur. So by respect to all these 3 kind of metal, we have the Frank Bedema, we have a Bomber Weber and Starkey Kastanov. So all this model is how the layer is formed layer by layer by layer. In some time, we have a formation of the islands is formed over here. That's why they become heterogeneous. Heterogeneous. It's not soft. It's not homogeneous. Okay? Right, next. Well, as I said, just now formation is mainly occurred by chemisorb and pergisorb. This is how. So for chemisorb, it's more toward to valence force, while for the pergisorb, it's more toward the intermolecular force. For example, like van der Waals force. Van der Waals force, for example. Right. So now we go ahead with the application of surface sign. What is surface sign all about? So from this figure, you can see, actually, the study on the surface is can be categorized into the several categories, like atomic layer, for example. So, say the first one, you got 1 to 5, for example, you got solubility, wettability study, catalyst study, functional. That is very sensitive surface. But we come in much thicker oxide, that we have oxidation, we have after contact, passive corrosion. When the metal is formed by corrosion, the surface actually from thin layer and then go to much layer, and then become very thick. That's why the formation start from nanometer range and then go to micron level range. All right, and then we have about thin film structure and so on, etc. That's all about that. Okay, that's why in the metal structure we have the starting from the substrate, and then we have the formation of the thin film. So in this context, it depends on the type of the material. If you deal with the ferrum, for example, we call it rusty. But if we deal with the silicon oxide, for example, it turns to another one. Like it's very useful for micro-electronic device thing. All right. So talking about this, we got the oxide layer, we have the component layer, and then go into the bulk. We have this. That's why some of my students maybe already know about this concept of lattice, the lattice in the bulk. The lattice in the bulk. So that's why in lattice sometimes you got the defect. So defect will be allow the gases to be diffused into the metal. So the inner side of the metal will be corroded because of the diffusion, because of the defect of the surface. Right. Next, we go to the next one. Now talking about the interface, this is the same thing. We got the silicon oxide, substrate, and the oxide, and then thin film. And the oxide is not only one, but the oxide can be categorized into another smaller part we call suboxide. Suboxide. That's right. Prof. Insan. You agree with me, Prof. Insan? Thank you, bro. Okay, next we have this layer. Now, there is one system we call focus ion beam. Focus ion beam system that will allow us to study the electrical section. Dr. Azli, yeah? Okay, now there we use argon, and then we bombard, and then we create a crater, and then we fill up, and then we can analyze it, and then finally what we can see a real morphology structure of lateral from the bulk, from the silicon sulfate down to CiO2 to silicon germanium and so on until the top. You see, that is the interface now, you see? That is a layer by layer by layer by layer, the interface somewhere on that. Okay? Next, we have also the same thing with the corrosion, metal corrosion layer. On the top, we have the porous layer, and then we have the salt layer, top layer, and then we got the laminate, and then down beneath that we got the layer. That's why, if you go to, you notice that sometimes when you use the spoon at home, the manufacturer claim that is stainless steel. But if you keep it in the sink for several months, it will be rusted. They rusted because of water, because of humidity. But I believe if you don't throw it away, you don't have to away. If you're rusted, don't throw it away. What you need the sandpaper and then grind it, and then until the metal reveal. Right, Prof? Yeah? You agree with me, Prof? Yeah? Some people they throw it away into the bin. Yeah. If we can remove it. If remove it, underneath there's steel. Then you can bending and then perform the electroplating. Back to be computer, something like that. All right, next, this is a rusty part, for example. I think everybody already know about this. And then talking about the corrosion, we got the resistor barrier. Some metal, we need to perform what we call alloying process. But introduce some amount of anti-corrosion particle, and then we start with the formation of barrier. Yeah, right. That's why we have the sensitivity. Sometimes we got layer of chromium. So the layer of chromium maybe become a defense to from the water or air to attack the steel. That's why we have this. This we call alloying. Right, in the catalyst, for example, catalyst. I think Prof Zawati is here. Prof Zawati, she's expert in catalyst. Prof, thank you, Prof, for coming. And I think in catalyst, for example, car exhaust combustion system, right? You got catalyst. That's why some car cannot be started because catalyst system. You got inside the catalyst. What you have the formation like this. We got sometimes a honeycomb, mineral wool, and so on. This is how they like. And we have the reactive material, for example. Yeah, this is called a catalyst. I think another professor who explained this, Professor Taufik Yap. Professor Taufik Yap from UPM. He's an expert on this. Yeah, expert in catalyst. Right, so this is for example of the catalytic system of a car. So you can see we use the ESCA. You can see that this ESCA is used, yeah, in this study. Next, in bioscience. For example, metal implant. Metal implant. So you got a fracture. You go to hospital. You go to orthopedic. The doctor will put the metal in your body, and then they join it, and then they. What happens if the metal is rusted metal? It's not good to our health. That's why we go to a metal implant, cost you a lot of money. Because why? We got to use special metal, titanium, like titanium, for example. They put into your body. Like even you go to dentistry, you get gigi palsu, right? Very cost you a lot of money as well. Because why? That's why that's also interaction between metal with our body. Because in our body, if you put the metal in our body, it's not even the flesh, but we got water, a liquid form in our body. Yeah, solid, liquid, also a gases in our body. Yeah, all right. Now, next, in hard disk component. I'm not sure whether we have the representative from ST Microelectronics, Mr. Zuhairi, is here or not. I'm not sure, but I invite you. Thank you, Mr. Zuhairi, for coming from ST. Give a clap to Mr. Zuhairi. Mr. Zuhairi, thank you for coming. He's from ST Microelectronics. Thank you for coming. So I think Mr. Zuhairi very well known about this, failure analysis industry, right? So now we're talking about this hard disk. We got a lot of, like now, the technology is SD, solid state, right? We have a Western Digital, right, Seagate, and so on. So you know how the technician or engineer detect the failure on the surface by using SPS system or ESCA scope. So this is for example of the spectrum. Yeah, you see over here, if the silicon was present at the ancestral level, so the end user will reject it. So how can we know about the contamination? Because this contamination happen in very, very tiny. You cannot see it. And even we talk about carbon in our daily life. Either you are noticed or not, everywhere is carbon. In our body also carbon. If you eat the sayur-sayuran, the vegetable, I've done it before. I asked my student to run with same that Prof. The vegetable contain carbon. That's why, yeah, carbon. Everything carbon. The daging is on the carbon. That's why the mumia in pyramid, yeah, they use the carbon dating to calculate because all carbon. We are surrounded by carbon. I try to find the Al-Quran where the evidence, is there any evidence? I try to find it. The carbon. We are made from carbon. Yeah, that's true. When you die, we become a carbon. A carbon. That's why carbon is very useful. Yeah, carbon is very useful. Right. Now carbon sometimes is not good. It's contaminated. That's why you cannot touch. Yeah. Clean surface with your hand. You have to use special gloves, a special glove. You touch it, the carbon is there. That's why in crime investigation, how the crime investigator do that? They're using carbon by fingerprint. Like from here, carbon, sticking the carbon. Okay, right. Next. Now when talk about, we got a lot of area. I cannot explain. You can have a look here. We got biosensor, we all things. Yeah. All right. Now I have to go a bit on this because my topic is covered on this. So let me explain what is it about. Yeah, I try my best to explain to you. When we talk about environmental, is something that we manipulate. We alter the surface of the material to become improved. In terms of the strengthening, in terms of the anti-corrosion barrier, and etc. In terms of energy binding, for example, like used in the solar panel. Okay? Right. So when we talk about the advanced material, so we can classify into several categories, like advanced alloy, we got the polymer, we got the biopolymer, metal, and then we got composite and etc. Yeah? Okay. Right. This is all about the metal, the advanced metal. Now, then talking about how can the engineer or scientist investigate or study, the study of the failure. How? By using X-ray. Since the atoms are compact, all atoms are blocking by another atom. We need special radiation that can allow us to study. That's why we have X-ray. X-ray is discovered by Wilhelm Conrad Röntgen in 80-something. He the first Nobel Prize winner. Wilhelm Conrad Röntgen is German scientist. Yeah, having that kind of X-ray, then the X-ray allows us to penetrate into the depth of the material. That's why we have XRD. From XRD, we can learn about the crystallography of the material. And also, nowadays, we got a latest technology until we can go to microscopy level, even nanometer level. So that is the function of science in this. Yeah. All right. Now, say one scientist understood fundamental atom rule, they could create entirely new material. Now we cannot, create the material without like rojak something like that. No, you have to investigate first. Yeah, right. Right now, talking about material, advanced material. Yeah, how advanced material change our life. Now, I think, we all of us. I think when I say very common example is mobile phone. Nowadays, mobile phones are very important. Yeah, mobile phone is very important. Underneath of the screen, we got the IC. The IC are very tiny. And I imagine, maybe someday, the mobile phone is not like that. Maybe the mobile phone to become a pieces of paper. A piece of layer, who knows? Because with the technology, become small. Yeah? Alright. Now, talking about the advancement of technology, of the evolution of this technology. So we need to consider from a material perspective, from the bulk to the quantum well, to the quantum wire, and then finally to quantum dot. Quantum dot. In my faculty, we have expert, Dr. Amira Sariati. She is expert in quantum dot. She graduated in, am I right, Dr. Amira? Thank you for coming, Dr. Amira. She is expert in quantum dot. That's why I mentioned her name then, okay? Thank you, Dr. Amira, for coming. And Dr. Fisha as well, okay? Quantum dot is very small. I think if you want to further about quantum dot, maybe to refer to Dr. Amira Sariati. Okay? All right, now, see, smaller and more efficient. That's the scientist or the engineer want. Smaller is better. Even the hard drive. Long time ago, they use, back sector because of hard drive. Now, no back sector. They use SSD, solid state disk, am I right? Okay. Then, smartphone and all these things. Now, this is how the advanced material change our life then. Right, there are a lot of application of advanced material. Yeah? Sustainable metal, material for medical, material for sustainable energy, for solar panel, for example, sustainable for polymer, for battery, for alloy, and etc. Right, so this is from the advanced material, then we go research, and then go ahead with the policy and funding and so on. I think Prof. Rabia, I think this is clear for feature about this, maybe if you turn to innovation, to something like that. Right, so I'm not going to explain in detail this, but I try to give the idea only, yeah. All right, then talking about advanced materials, so you see from the bar chart, what you can see, there is an increment in the drastic increment, steady increment away from 2022 up to 2023. Around the world, the market of the material to become increased steadily like that. But you see, in terms of the advanced material in the globe, so you see, come from the country like from America, South America, Europe, and then got Middle East, and then Asia Pacific, so on. And there's every single country have their contribution in this. Yeah, you can read on down there. Right, growth factor, what makes the advanced material to become very important? The factor is, number one, is renewable energy. Now, renewable energy are very important because in order to reduce the pollution. That's why we have an EV, car battery. Why I go car battery rather than use a petrol? Right, because EV is very clean. Am I right? And also, renewable energy. Sometimes got blackout, at least got the backup power from solar panel, right? Now renewable energy, we got a lot of renewable energy, and then there's a demand of renewable energy, medical devices, smart material like mobile phone, as I said just now, and also an aerospace. In Malaysia, we have one factory in Batu Berendam, right? Batu Berendam, I forget its name of the factory. And also we have the electric EV or EV now, yeah. So all these have make the advanced material to become very important, yeah. But we don't know afterward what kind of industry will happen after, yeah. So over here we have distribution of publication. Now in publication, in terms of number, we can see over here there are so many terms that is of the advanced material that cover under the material science one. So, we mean that most of the author who read about, who publish on the advanced material, so normally they are focused on material science perspective, and then followed by chemistry and down to that. Okay, and in terms of the publication in from all over the world, you can see the position from top 24 country. You see Malaysia is there. Malaysia is somewhere around there, 722. Right? Those are just compared to Chinese. Chinese, they are good compared to Europe, and then later Europe and US followed by India and so on. Malaysia, we are somewhere around there. When we talk about Malaysia, I think we need to touch a bit on this. There is a National Advanced Material Technology Roadmap. 2021, 2030. The blueprint is there. You can see from starting from national for IR policy, and then we got the last one then. And the most important element in this are considered like number one, graphene, netinol, rare earths that we're talking about liners, rare earths, yeah, rare earths. And then we have the microcrystalline cellulose polymer. So all the ingredients that we consider can contribute to the encouragement of the advanced material in Malaysia. And the 4 goals there, yeah, you can read that. Right, and this is the material, kind of material, the forecasting of material. Yeah, you can see here, in up to 2028, you can see, yeah, they forecast that the advanced material that have a high demand will be metamaterial. You see, in 2028, and followed by plastic, and then composite material, and down to there. Why metamaterial? Because metamaterial is used as the antenna, or maybe used in communication. Maybe communication become very important in the future, so that's why the demand of this element become very important then. Okay, right, next. Right, talking about this application of the advanced material in Malaysia, we have aerostructure. The champion of this is, you can see the company there, Torre, Cabo, Antakanaka, and so on. And then carbon capture, graphene, nano, and so on. So this is all the companies there, yeah? The advanced material is showing there, the element. Up to, you see, polymer, Petronas, and then rare earth. Rare earths? What is the use of rare earths now? Right, now, talking about rare earths, you go to the periodic table, there is a series of lanthanide. Lanthanide and actinide. Lanthanide and actinide is rare earth metal. Yeah, so the element that they extract in the liners is mainly lanthanum. And then at the end of it come up with monazite. Monazite is a part of thorium, and it is radioactive material. That's why they are do some investigation on the area. And the use of these rare earths is for most common application, power magnet, optical, hard disk, battery, and etc. Okay, so all this. Right now, we got this company, and then also got IPTA, some IPTA is there, UTHM is there as well. So UTHM, got UTHM or not? Yes, UTHM, that to ATEX, UTM, UKM, and so on, and all the combination of the company. Right, this is the export, import, export. So here how we can improve our economy then, in terms of advanced material in the future. Yeah, some material are import, some material are export. Yeah, okay. Right, so talking about this advanced material, yeah, we have 3 categories, which is surface, structure, and feature material platform. So now, because of my lecture, we touch on the surface. Now, surface, under the category of surface, we have protective coating, we have functional coating, dynamic coating into imaging adhesive. So all categories are as follows. We got a lot of things, yeah? Anti-corrosion, anti-faulting, ceramic. We have Prozaki, my dean is expert in ceramic. Prozaki, yeah? Ceramic. So ceramic is very useful then, okay? Right, and then so on. Right, so from this, all this, okay, we need to have a method to modify the surface. How can we modify the surface? By using thin film technology. By using what they call thin film deposit. Sorry. Okay. Now we have the technology in UTHM. We have the magnetron sputtering, sputtered in Min Asasi. I think Prof. Nafariza and Prof. Khairul, they are expert on this. Prof. Khairul, right? Yeah, sputtering method for sputtering for Nafa as well. Now, using this thin film deformation. So, what is of this? In order to modify the surface, to enhance it. So we have the two things, physical and chemical. There are two methods. Yeah. So starting from the thin film down to thicker film. So this is in order to, we embedded in this thin film technology, we embedded the material to improve the surface. Okay? Right. Next, the application of this. So the application is covered by this, all this. In healthcare, interfacial, environment, energy, and even it covers the IoT as well, thin film technology and the IoT. I noticed that nowadays the people keep on talking about IoT, right, Prof Rabia? IoT are very important. This is now you can see from here the importance of the surface study also have related with IoT as well. And yeah, now we have the material. Yeah. Now what is the problem? The problem is sometimes when you use a mobile phone, your mobile phone can be last about a few years and then kaput. Am I right? Become kaput, you see. You cannot use. Why? Because the failure of the circuit. It comes from maybe become pollution. Yeah? So the circuit is not long lasting. So therefore, we need a failure analysis. So in the industry, I think Mr. Zuhairi, he always keep in touch with me. Yeah? We chat each other to discuss about the failure analysis for example in ST microtronic using SPS. Thank you for coming, Mr. Zuhairi. Yeah? Thank you for coming. Right. Then, from here, in the perspective of failure analysis, why we need failure analysis? Because failure analysis evaluates failed component. Before the product is released to the market, we need to ensure the quality. So how can we do? There is no defect. So therefore, we need to perform failure analysis. In failure analysis, the schematic order is like this. We have the cost information, microscopic inspection, sample, select sample, microscopic examination, material testing, interpretation, and then from there got report. Then Mr. Zuhairi will submit the report to his boss then, right? Right. Okay, next. Now, we need to, since we cannot see the failure with our naked eyes, of course you cannot see it with your naked eye because it's very thin. Therefore, we need special device to investigate on this by using advanced technique like Raman scattering and also FTR, and so on. But I need to highlight on SPS in this lecture then, okay? SPS, all right. Right, they're talking about the concept of the spectroscopy. So most of the spectroscopy will contain with three things. The main thing is the source, the sample will be loaded into the vacuum. There's a vacuum pump underneath that. And then we have the source to extract the sample. And then we have a detector. So the source can be either monochromatic X-ray, electron is a particle. That's why in modern physics, I think my student who learn modern physics, we have one principle. You call as duality principle, de Broglie principle, or sometimes they call de Broglie principle, a duality principle. The particle can become a wave can become a particle, right? Okay, now, you have X-ray, a photon, but electron is not photon. Electron is a particle. And then we have ion is a particle of course, and the detector, and then one after, the source, either X-ray or electron bombard on the surface, and then there will be formation either electron, photon or ion from the sample, and this kind of thing will be detected by the detector. And the environment is under vacuum. Why under vacuum? I will let you know later. And why most of the equipment cost you a lot of money? Like SPS cost a lot of money then. Several million. What makes the system become very expensive? Because of this reason. So, in XPS analysis, normally we talking about is the schematic diagram of the X-ray penetration on the material. So, the shape like the onion shape, you see? Right? So, the EDAX, SEM-EDAX, so on. But we are not talking about deep, we are talking about on the surface, which is at the 1 to 12 nanometer on the surface, uppermost. Like you have an onion, You peel out the skin. The skin is like the surface, the thin film there. Very easy analogy, you see. Yeah? Right. Now, this is a technique. I pass this one. So, the laser diamond, I pass this one. So, now we talk about the vacuum. Most of the high-tech, ESCA, operated under vacuum. When I say vacuum, okay, vacuum, there is no gases. That's why, you see a lot from the video of you go to Harvard, you go to Cambridge, you go on, say NUS or whatever, at the university, who have a sophisticated machine like this, you might be able to see there are a lot of things like this. What is this? It's like spaceship. This we call a vessel. A vessel. V-E-S-S-E-L, or a chamber. Vacuum chamber. It's made from very strong material, from stainless steel. And covered by, we allow you to see what I got inside there. I got the mirror, special mirror over there. So now the question, why vacuum is very important? That's why in Pago, we have clean room, but to me it's not clean. Still not clean. Yeah? Yeah, clean is clean, but still, yeah? Right. Because the surrounding is only gases. Right? It's not vacuum. Now, when you talk about the vacuum, why vacuum is very important? Because it enables to make sure the sample surface become very clean. Very clean. That's why you see, go to the Western Digital, Seagate factory, you can see all the engineer wearing a special clean room suit, something like that. Prof Azman, yeah? Prof Azman no better than me. Prof Azman is from IMEN, UKM. Please give a clap to Prof Azman. He's a champion in microelectronics. That's why I call him. Thank you, Prof, for coming to my lecture, Prof. Really appreciate. Right, yeah? That's why you can see a lot of people in the factory wearing a special suit like astronaut. It's not like astronaut suit. That is the clean room suit. Okay? In order to ensure all clean, and also allow, second one is very hard to explain, but I try my best to explain to you. In order to permit the use of low energy electron and ion phases experimental technique without undue interference. What does it mean? With the gases, what does it mean? It means the electron will not having any collision with the gases. It's not lost the energy. Now imagine, very easy to understand, imagine we are in vacuum. Imagine on the surface now. We are in Payaraja, yes, Payaraja. There's vacuum. Now we are dying then. Vacuum, we cannot breathe. Now imagine we trigger electron from Parit Raja. How far I can go up to in 1 second? If there is vacuum. In atmosphere cannot. Atmosphere it can be only several. It stop. Because a lot of gases, a lot of sources of gases we can see. In vacuum, that electron can go from Johor Bahru to maybe to Penang in 1 second. Very easy to understand. Okay? That's why in the system we need electron to go to detector. If the electron collide with the atom, they lost the energy. Yeah? Okay, right? Next. How long it take now? I hope under 2 hours from Zaidi. I still got a lot of slides, but I try my best to speed it up. Let me know, yeah? Let me know, yeah? Let me. Okay, vacuum. Why vacuum? I love to show you this photo. Very good analogy. Now, I can say, with thanks to our God, thanks to Allah, because we live on the earth. All of us, all of the humankind. Either you realize or not realize, we have to say thank to Allah. Why? Because we are living at the equilibrium condition, at the atmospheric condition. We can breathe. We can breathe at 101.13 kilopascal. We can breathe at the pressure of 101.13 kilopascal. That is our pressure. That's why sometimes we got the fever, flu, we check the blood pressure. Yeah? Okay. Right. Why? I say we are in the equilibrium line. The earth are equilibrium line. Nowadays, NASA try to find the other planet like Mars, but the situation in Mars is totally not difficult, not similar to Earth. It could be no oxygen, could be rusty and so on. Yeah. Now, why I say that? Because in atmosphere, you compare to, you see now, that is a photo of outer space. Start from troposphere, stratosphere, up to mesosphere, up to exosphere. Until you see there is an international space station over there. What is the pressure over there? Now on our surface of Earth, we are somewhere around 101.13 kilopascal. 0.3 kilopascal. Yeah? Or 100 times by 5, negative 5. How about the outer space? Negative 16 Thor. Negative 16. So what happened? Why astronauts have to wear special suit? Because the suit, stabilize the body. There is a pressure similar to the Earth. If something leaking, what happened to the astronaut? Exploded. Why? The blood pressure. The blood pressure, you see, from formula, pressure. What is pressure? P equal to F over A. Force divided by area. Our nerves are very tiny. If the nerves are tiny, the pressure becomes very high. So in our body, you count how many million of blood nerve in our body. It is a pressure. That pressure in our body are heading upward, but is stabilized by atmospheric pressure. Now you understand what I'm trying to say? Yeah, I hope everybody clear on this. Yeah, our pressure, the body of pressure of our body are equivalent to the pressure of the atmosphere pressure. But if you go to the atmosphere, you go to outer space, your body become exploded because the pressure will high in your body and explode like boom, kaboom. Okay? Now, if you go to underneath of the ocean, like we have the previous incident happened. It shot all over the world. The incident of Titan. How they try to go to the Titanic, right? So what is pressure over here? Down to here. You go Peru, they got here, down to Mariana Trench. The deepest depth in the ocean is somewhere around Mariana Trench. It's very close to Malaysia. It's somewhere around nearby Philippines. That is very deep. Now you go much deeper, what happened? It's like your body have been what? Stuck by a ton of material. It's squeezed. Your body becomes squeezed. This make the Titan, all the Titan, not survive then because of that. Pressure very high. No way to go for us. If you go downward deeper, you're dying. You go higher, you're dying. Even you go to Cameron Highland, sometimes you feel your hair, your ear, your eardrum, your pain go here, right? Because of pressure. You go to Everest, of course, the climber need to have a tank, bring oxygen. Right, next, this is talking about pressure. Now pressure, low pressure, high pressure concept, we have that. Now, when talk about the vacuum, is anything that is devoid of matter. Nothing exists. That's why the sun light can reach to the surface of the earth, because there is the vacuum. The electromagnetic wave can propagate on the surface of earth because it's a vacuum. When we talk about this vacuum or the outer space, there is minus 16 Thor. But the type of pressure, you go to petrol pump station, for example, you want to pump your tire. There is a unit, sometimes, PSI unit, right? Some people know, but some people doesn't know what PSI is meaning. Okay, now, the unit of pressure, in atmospheric pressure, we can use all this unit. One atmospheric pressure equivalent to 700 cc Thor. The name after Torricelli. Torricelli is the Italian scientist. Torricelli, the name of Italian scientist. And then 101 millibar or this is our pressure, yeah, 1013 kilopascal or Pascal. Then we have 14.7 psi, and then got all this, yeah, and the torr unit, the millibar unit, and etc. Right now, vacuum condition in our ESCA scope, every single survey technique, all the equipment will be operated below than 10 to the power by negative 9 torr. Very similar to, I think it's not similar to atmospheric pressure. Sorry, not similar to outer space pressure, but at least we have. Nowadays, the scientists try to get another range up to extreme, yeah, much lower than this. All right, now this is it's too technical. This thing I think too technical, but never mind. I'll explain a bit. How can we have a vacuum? The vacuum that I'm saying now is not like vacuum at home. The vacuum at home is even you put the coin, the pieces of paper, right? The paper will be sucked, you know, right? But the thing, you imagine if the vacuum is much powerful than this, than your vacuum at home. Even the dust, all the dust, even the carpet can be all the tanggal then, okay? Right, then see, they use a lot of pump, combination of rotary pump, ion pump, turbomolecular pump, and titanium summation, all the pump. The combination of the pump, this is how the pump look like. It's like a rocket engine or, you know, aeroplane engine, something like that. We got a rotary blade over there. So one after is rotating, it is sucking all the gases to be inside there, okay? So it's quite technical. I think I passed this one as well. So I go ahead, so this is about the vacuum region and so on. Right, and so on. This one I say low pressure, high vacuum, high pressure, low vacuum. That's okay. Right, there is the equipment or device. In order, then how can we measure the vacuum? By using a gauge. This is how to run a gauge, not goggle. A gauge. A gauge. Yeah, a device is used to measure the pressure inside the chamber. Okay? Right, by using this gauge. There are a lot of gauge. We got a YouTube gauge, Bowden gauge. But in most of the advanced system, they use all these gauge. Starting from Pirani down to here. Down to we got Bayard Alpert. Not Toyota Alpert. Bayard Alpert. Okay? And so on. Then all these are working at the nearly negative 10 torr. Yeah? And then we have the pump, all the pump. The pump, the concept of the pump is very easy. Like you are running 400 meter. The first button, run. And then pass to another button. Turn to another runner. Turn to another. Until they reach to negative something. That's how it's working. Yeah? Alright. And alright, now last one. We got ESCA. What is ESCA stand for? Electron spectroscopy chemical analysis. This is the device that we use in order to study on the surface at the range of surface at 1 to 10 nanometer. Now you can see from the photo here, you see that is a substrate, and then we have the sources like X-ray, you got UV lamp, and synchrotron, so on. And then this radiation, we interact, we bombard on the surface, and then we have the what they call a process that we call photoelectrons process. And then we got the electron, and then go to the detector, and then finally we have that. Now, what is the main important one here? The electron. The electron are very important. Now, you look at on the electron. Now, electron is around the nucleus. Inside the nucleus, we have a proton and neutron. Proton and neutron. Proton combined with nucleon. The proton and neutron, when they combine, we call nucleon. Nucleon. Nucleon is a combination of proton and neutron. But this nucleus is surrounded by electron. Now, when we talk about electron, electron is a cloud. Yeah? You consider it as a cloud. So, you can see from here, if you look at on the comparison between the atom with the electron. Atom is about 10 to the power by negative 10 meter. Nucleus is about this. Finally, you can see, electrons are very tiny particle. Very tiny. Okay? Now, in order to explain much detail, I think we have to look at on this video. I have 3 videos, about 50 minutes, something like that. Okay? I think it needs to play. It's not working. Now focus down to the hair at 100 micron. Okay. Now see a cell. You can see the cell now. And microfiber. Yeah. Microfiber again at 10 nanometer. Photofiber at 2.8 nanometer. And we have keratin, yeah, 2 nanometer in the body. All this, I say carbon in our body, right? Carbon there, right? Carbon. The carbon as well, yeah. Electron. Now you see the electron now is focused more down to electron now. See the orbit. The nucleus. Now you see the nucleus now. Yeah, that's the nucleus. Inside the nucleus we have, you can see, much smaller. Proton and neutron is there. Okay. And then photon and neutron, we have another one, what they call elementary particle. Yeah, elementary particle that we call as a quark. A quark, that is elementary particle. And yeah, talking about this, yeah, we need to know about more about electron now. So we go ahead with another video.
The best way to picture an atom is as a compact, dense nucleus encircled by buzzing, orbiting electrons. This image prompts the following query: how do electrons continue to spin around the nucleus without ever slowing down? This was a big question at the start of the 20th century, and the search for an answer led to the creation of quantum mechanics. After countless experiments, physicists were just starting to piece together a coherent picture of the atom in the early 20th century. They came to understand that each atom was composed of a tiny, negatively charged cloud of electrons surrounding a dense, heavy, positively charged nucleus. They then proceeded to build a more thorough model with that broad picture in mind. The solar system, which has a dense nucleus surrounded by a cloud of smaller particles, served as the model's initial source of inspiration. However, this model introduced two serious issues. One is that an accelerating charged particle produces electromagnetic radiation. Also, since charged particles accelerate during their orbits, radiation should be produced by electrons because they are charged particles. According to researchers at the University of Tennessee at Knoxville, this emission would cause the electrons to rapidly spiral in and collide with the nucleus as they lose energy. In the early 1900s, physicists predicted that such an inward spiral would occur in less than a picosecond, or 1/1,000,000,000 of a second. This was not going to work because atoms obviously have longer lives than a picosecond. The nature of the radiation was a second, more subtle problem. Atoms are known to emit radiation, but it is known that the frequencies at which they do so are very distinct. If this model of the solar system were true, an electron in orbit would give off a wide range of wavelengths, which is not what scientists have seen. Famed Niels Bohr, a Danish physicist, was the first to suggest a fix for this problem. He proposed in 1913 that electrons in an atom couldn't just choose any orbit. The Nobel Prize citation entry for his subsequent award states that they had to be locked into orbits at very precise distances from the nucleus instead. He also suggested a minimum distance an electron could travel before it could no longer move away from the nucleus. These concepts didn't just appear to him out of nowhere. According to the hyperphysics reference page at Georgia State University, the German physicist Max Planck had suggested that the emission of radiation might be quantized, which would mean that an object could only absorb or emit radiation in discrete chunks and not have any value it wanted. However, the smallest size of these distinct units was a fixed quantity that became known as Planck's constant. Scientists used to think that these emissions happened all the time, which would mean that particles could give off radiation at any frequency. The units for Planck's constant are the same as those for angular momentum, or the momentum of a circle-moving object. Bohr then applied this concept to electrons orbiting a nucleus, claiming that the tiniest orbit an electron would have an angular momentum equal to 1 Planck constant. Higher orbits may have a Planck constant value of 2, 3, or any other integer multiple, but never a fraction of it. To fully comprehend why electrons have such a small minimum orbit and clearly defined higher orbits, quantum mechanics must be fully developed. Like all elements of matter, electrons exhibit both wave and particle behavior. One way to think of an electron is as a tiny planet that goes around the nucleus. Another way is as a wave that goes around the nucleus. In a small area, waves must abide by specific laws. They must be made of standing waves that can fit within the space, they cannot have any wavelength. Similar to when someone plays a musical instrument, only specific wavelengths will fit if the ends of a guitar string are pinched down, giving you the distinct notes. Similar to how an electron wave around a nucleus must fit, the first standing wave of an electron indicates its closest orbit to the nucleus. This image would continue to be improved by quantum mechanical developments in the future, but the fundamental idea remains: because of its inherent quantum mechanical properties, an electron can never be any closer to a nucleus. However, there is a completely different approach to the problem that makes no use of quantum mechanics at all. Just consider the various energies at play. An electron in an orbit around a nucleus is electrically drawn to the nucleus and is constantly being drawn in that direction. However, the electron also has kinetic energy, which propels it into flight. These two balance each other for a stable atom. Actually, an electron's total energy, which combines its kinetic and potential energies, is negative. This means that if you want to remove the electron from the atom, you must give it more energy. The planets in orbit around the Sun are in a similar situation. In order to remove one from the solar system, additional energy would need to be added to the system. Consider an electron falling toward a nucleus because of the attraction of its opposing electric charge. But it will never get to the nucleus because of the laws of quantum mechanics. Due to its orbital impasse, it becomes stuck. But since the system's total energy is negative, it is stable and stays together to make an atom that lasts, so physics lets this happen.
Okay, we have another one. Last one, this one, yeah? Okay, this is concept of atom, yeah? Another one. Concept of element from the periodic table. You can see is the radius, comparison of the radius from hydrogen with 1 electron, and then increase 2, 3, and so on. Now become bigger and bigger and bigger with the high density of the electron. The electron is the orbital is represented by the green color, the red circle. How do you like, yeah? This is top in the middle. Bigger, bigger, and bigger, yeah? Okay. Right. I think I cannot bring the electron here. That's why I show you the photo. That's why the video. I will not going to bring the electron, you know. How can I explain to the electron? Electron very tiny one, see? Right, now, talking about this, why SPI very important? My answer normally I have to answer. Number one, because of the vacuum. Yeah? Number two, because the machine, the system have been discovered or established by 2 great Nobel Prize winners. I can say 3. Wilhelm Conrad Röntgen, the first person who discovered X-ray. The second one is Albert Einstein. Albert Einstein discovered photoelectric effect. Though this effect is not only used in SPS or ESCA, but also useful in solar panel as well. Right? That's why we have solar photoelectron. That's why solar panel normally we call as PV, photovoltaic, right? So now Einstein have discovered this phenomena in 1921. It allowed him to be awarded the Nobel Prize. And second, we have the first person who set up the SPS system is Kai Zeben. Kai Zeben is Uppsala University, Sweden. So I still remember during that time, he passed away in 20 July 2007. During that time, I am still in UK. My viva is somewhere around October 2007. He passed away 3 months before my viva. But I never realized he's still alive during that time. And then I see the article, okay, now see. All right, now Kai Sieben is from Uppsala University in Sweden. These two. So the concept of this SPS or ESCA come from the kinetic energy of electron. Different from the kinetic energy of electron, because every single electron have their own energy. I think I show you how the electron look like just now, yeah? Right, so this is the Nobel Prize winner. I mean, behind the SPS, there are 2 greats, physicists and chemists, okay? Right, now what is happen actually? What is a photon? See, this is very easy to understand. You see, one after the photon is bombarded on the atom, so the energy from the photon will be absorbed by the electron. So the electron will absorb and then will be released as the electron. That's why we call photoelectron. Photo is referred to photon, electron is referred to electron that release. Another one, we have another one is OJ effect. OJ effect is the same process, but it's only happen at the uppermost layer there, uppermost level there, okay? Right, one single electron rejected, known as OJ. So we got 2, OJ and photon. But in my lecture, I only focus on this photon, okay? Now, what happened is like this. One after is a sample irradiate. So the X-ray will be penetrate from the surface down to the bulk. So one after is absorbed, and every single electron, the atom on the underneath that. So see, this X-ray will interact with the atom, and then the electron will be released from the underneath that, even up to the uppermost layer there. So the easiest one is uppermost layer. The electron from uppermost layer is easy to escape compared to the bulk of the material. So all these electrons will be useful in order to what? In order to acquire the kinetic energy, and then we can plot it as the photoelectron spectra. So what SPS can be contribute to, for example, like in catalyst science, for example. So number one, we can analyze the surface or composition. We're not going to allow, if you use another method like SEM-EDAP, it's not the same. It's not the same. In terms of penetration, it's not the same. It go much deeper for SEM-EDAP. SPS, you go up to several nanometer. You can determine that using this, and then oxidation state. Because sometimes the oxidation state, the layer by layer will change. So now, the oxidation state we change then. For example, zinc, Zn2+, 4+, and so on. Yeah, go to film. Then go surface electronic state, and then thin film analysis. All this is the X-ray can offer. So this is an example of the what XPS can offer. Chemical state spectrum, we can determine the hydrocarbon. Now this is the photoelectron signal, you can see that. The signal normally like that. Yeah, it's quite similar to another kind of yes, they're similar, but the thing is, in terms of where you get the data, the signal is not similar. Yeah, right. Now, by using this, by using the binding energy, then we can determine the species or chemical state for hydrocarbon, the ethyl alcohol, etc. And also, we can perform the depth profiling analysis. By using depth profiling analysis, we can study on the interface, what is happened from the uppermost layer down to the bulk of the layer. And then also the surface scan, the ion etch, and so on. So all these are examples. And for the final concept of this SPS, normally, it's covered by like this one. You got lots of things. You got 2 chambers. We got the preparation chamber over here, and then we got the surface chamber. Surface energy chamber. So the transfer chamber is the chamber that allows us to load our sample. But the analysis chamber is covered by multi-technique. To me, in order to make analogy very simple, like Medusa. You know Medusa? The head with a lot of snake. That's it. One chamber, we cover a lot of things, a lot of method. Like Medusa, you know Medusa, yeah? Ladies, a picture lady with a snake on the hair and on the head. Okay, then we've got one head, one chamber, come up with a lot of technique. UPS, ultra photo electron, X-ray gun, we got secondary electron detector, we got FESAM, we got X-ray gun, ion gun, and etc. That's why it makes so special. And why so special? Because it's not at atmospheric pressure. Inside there is similar to outer space. Similar to outer space. But it's not similar. Outer space is about 10 to power by negative 16. But this can reach to negative 11 Torr. Still higher than compared to the outer space. Right now, how is it like? This is my system that I used long time ago. You see a lot of things there. Sometimes I have to fit on my own, by the way. Right? So you see a lot of things. You cover lots. Yeah? You got OJ gun and so on. You got manipulator. But this is the oldest one. The system that I use is the oldest one. Yeah? So you got the X-ray gun over here. The back there. And then got the data acquisition system. The photo electron micro preamplifier. We got the photo electron detector, and etc. You got the manipulator here. Because this manipulator is like a robot hand. It's like a robot hand. In order to robot hand, you have the manipulator. We want to move your sample in the azimuthal direction, 3D direction, X, Y, Z. Okay, this is the one that I used long time ago. No, yeah. I think during my study, I struggled too much on repairing. Yeah, a lot of things. That's why. Now I have to feel on my own. Does it inside what you have inside there quite similar to other method? I'm sure. Right, you got a stop and so on. You got an X-ray gun, ion gun. This ion gun is in order to remove the contamination. By bombard with ion gun, we can sputter and can clean up the sample then. Alright, this is the chamber whereby the electron signal go. Yeah, right, and then this configuration, and this is the X-ray notation. In order to understand on this, you need to have a good knowledge on quantum mechanics. Quantum mechanics, yeah, quantum number. So we got SPDF number. Alright, so we have two kinds of method, either spectroscopic notation, this is for SPS, and then we got X-ray notation, this for OJ. So I think I'm not going to explain in detail about this, it's quite technical, yeah, right, and then the same, right, regarding to the how SPS can acquire the spectrum, because of this, the atom is there, this is your nucleus, and then the electron is there, the electron is surrounding here. Now, all the signal acquire according to the position of the electron. Now, why the 4F become very high is mean the density of electron is there is high. More electron is there. That's why it makes this the photoelectronic signal become very high then. So the pattern is like this one. This is the way how we determine it. Got kinetic. In the atom, the term of how the electron is bonding is respect to binding energy. Binding. But one after the electron is released, we refer to kinetic energy. Right? So this is orbit splitting. So I'm not going to explain detail this. Right? This is how the SPS spectrum look like. Yeah? We got spec signal like this, and then we have doublet. Doublet is like a horn, like cow horn. You see, got double. Doublet. Okay, the signal is normally like this one. Right, and there is a method that we call angle resolve. Angle resolve method is the method that allows us to study on the interface. By tilting up the sample. When after you tilt up, so what actually happen by using the manipulator, you can see, if your X-ray bombard over there, your sample are normal at angle of 0 degree of angle respect to the surface, then see the electron will release something like that. But if you tilt up at the 45 degree of angle, then the electrons bombard like that. Then how it happened? It's happened in this one. So it refers to this figure. So at 0, the diameter very small, but if you tilt up to grazing angle at the 80, so become elliptic. So the area become much wider, and also the lateral, you see, become deeper, from deeper part to dive part to small part. Okay, right. So that's why make SPS become very important. So this RSPS is a method how can we can determine the what you call the interface study. Yeah. So by using this one, right. And also respect to the XPS. Now everywhere you go now, SPS is all over the nation now. We have SPS listed here, from National University Kebangsaan Malaysia, Amret Kulim, and then up to 2018 we have one system in Pago, and then recently in UMS they managed to get one. Got the Ulvec Pi. So everywhere they have SPS, I will be there. That is one after I returned from UK a long time ago. I think Pro Instance you remember this photo. Pro Instance can imagine how I can walk with my walking stick long time ago, Prof. Yeah. So I still put the photo. Yeah. So during that time I remember this SPS somewhere around your faculty then. It's no longer in cream yet, right? Okay. Now see, Pro Amba is somewhere around there. Pro Amba Yarmo is I already. Now this is the system that we have in UKM. Yeah, 4.3 million. Right? And then we have in UTP. Last 2017, UTP in to give deliver a workshop there. So that's the one we have in UTP with Mr. Hazri, the technician over there. I am somewhere in front of the central lab, UTP. Yeah. It's a very compact one. It's not like the one that we have. It's like this one is much suitable for factory users. Yeah. Okay. I think for ST if they want to buy better, I think this kind of XPS is good enough. They're very compact, not bulky. This bulky one, the Amrex about 3.5 million. I was there. We probably remember this professor from UPM. Yeah. So I was there with Mr. Hazi at the back there. Yeah. And then in USM, they got 4.5 million. I was there with Mr. Tan. Mr. Tan is an expert from Singapore. Yeah. We every single workshop during that time, we collaborate to each other. So, right. Okay. Mr. Tan from Singapore. And then we have in UTM, 2.3 million. It's UIRL. The person in charge is Puan Amy. Yeah, Puan Amy. I think Pro Zaidi, our chancellor, no. Our chancellor, no. Our vice chancellor, no. Who's Puan Amy? So yeah, this is the one in UTM long time ago, 2.3 million. And then in Mimos, they have one. Puan Bajura at the back there. Yeah, that's me. The material, this is very compact. This is Pi Quantra. Yeah, Pi Quantra. 5 million, I think something like that, 5 million. Because, and that's ours. And we delivered in 2018 now. So this is my meeting with Dr. Jonathan from Kratos, Manchester, UK. During the training, yeah, so that. Yeah. This is the one that we have. This is the latest technology from Shimazu that we have. Inshallah, by end of this year, I think the SPS is on the way now. So one after in the way now, afterward we can use it. Okay, inshallah, okay. Right? And then this is the one that we have in UMS. UMS they have, under that Professor Datuk Taufik Yap. I still remember Datuk called me to get a consult to SPS. And then finally Datuk buy this one. 5 million, UMS one. We have got, but I'm not been in UMS yet. Inshallah coming soon. Yeah, coming soon I will go there. If possible, Prof. Yeah. And then go there, I will selfie with the machine. All right, that's me again during the course at the UTP with the student of UTP over there. Okay, that's me. And then I also deliver a lecture in USM at Nibun Tebal. I think Prof. Zaki know at Nibun Tebal, SRC, Nibun Tebal. So, Puan Khairi over here. Puan Khairi invite me to give a talk with, together with Mr. Tan. So, I surrounded by postgraduate, I don't know, postgraduate lecture during that time. They already graduate, I reckon, 2013 at SRC. And then at UTM Skudai, also delivered my speech. The one, okay. right? Okay. And then this is, I think, the first event that I involved, whereby Mimos Sirim Amrek called me to deliver a speech on SPS. I think nearly 100 scientists all over Malaysia. That's me in front there. With my old working, my old chair, my old one, my old chair. Okay, that's one in 2011, something like that. Now, if UTHM as SPS, now UTHM SPS, because I think I want to say thank you to Datuk Noh Dalimin, Datuk Wahid, I think Datuk Noh, I think I give a suggestion with Datuk Noh long time ago when I've returned to ask Datuk to buy our SPS. My intention is to put UTHM name to be same level with RU. I hope Pro Azman don't marah with me, okay? Okay, I want to put UTHM to be equivalent level with RU. That's why. If we having a SPS, then we are UTHM nearly equal to RU. That's my intention. Now we having one. I'm looking forward to that system will be operated. Inshallah. Dato and she keep on asking me when the system can be operated. Inshallah, I come soon. Now SPS around the group. Why? If we are having SPS, if UKM having UKM have your SPS, Pro Azman, UKM have SPS, it means we are similar to world ranking university. Like NUS, they have SPS. And then Department Chemistry of Science. In Nanyang, they have SPS. Yeah? And then in Cambridge, yes, they have SPS. At Maxwell Laboratory. And Oxford, they have that system, thermo. And Bristol, my alma mater, of course, have SPS, where I come from, SPS. And then Harvard having SPS. You see, as I said, the surrounding by the flash with a lot of things there. Yeah, very sophisticated. Yeah, in Stanford, in MIT, in Nagoya, Prof Nafa is not wrong, Prof Cairo, Nagoya, Japan, in Queensland, Australia, in Sydney, Australia. So meaning now, what I'm trying to highlight, by having SPS, I think our research can be up to the international level, similar to other high prestige universities around the world. And the chance for us to maybe publish in the high impact journal is very high. So talking about this is the nature, I think I passed, this is too technical. Yeah, I passed this one, and then I straight away to the application, I reckon. So in terms of the application, this one of course, I got 200 something. So this is how the way we deconvolute. This is quite related with mathematical term. Yeah. So the time now is already 12 o'clock, I have to stop, but I think it's now. Okay, this is the way how we study on the interface. By having that angle resolved, finally we can come up with the model of this one, something this interface. Yeah. We know where the position of the layer. Yeah. So even we know about the mechanism, how the formation of the layer. And it's not only that, but also see, for example, this one, yeah, the contamination on the surface. Okay, over here, this is spectrum from the contamination. This is a spectrum from the second layer with the iron and chromium oxide layer over here, and then down there from the stainless steel, and then up to nickel, and etc. Meaning now, we allow us to, by using the angle resolve, we can study on the layer by layer, yeah, or lateral cross-section, yeah. Right, the same thing happened to this is an example of the film for the gate dielectric, and then RSPS for profiling, yeah, right, and then this is solar panel, from solar panel, how we perform, yeah, from the surface to the bulk, how they change in the atomic concentration one. Right, now example, we got a lot of example in biology. Biology like wounded dressing, for example, like for glove, yeah, and then we have for antibody and so on. And for catalyst, for example, oxidation of cobalt base catalyst, and then maybe on the metal oxide, Yeah, method of cell formation for catalyst, something like that. Right. For defect analysis. So maybe in failure analysis for adhesive failure, yeah, sticking. Something that's sticking on the material. So ESP investigation on printed paper. For example, printed paper, you can see over there how the signal for the paper, for the inkjet, for the laser paper and so on. You can display. And then also the surface degradation of the painting. The painting there, you see how the painting, like Nippon painting, the quality of the painting, we can study using this SPS. And also with for some other electronic part, like we see, like HK dielectric material, and then we have, I said, like silicon and so on. Right. And microelectronic. Nowadays, see, you go to Batu Pahat, BP Mall, a lot of television. Television nowadays, they no longer using plasma LED, they use OLED. OLED, right? I'm not mistaken. Well, actually, in OLED layer, you see, the layer is something like that one. A C layer, cathode layer, emission layer, etc. And of course, because of these very tiny part, yeah, behind that. So of course, they use the SPS for failure analysis. Yeah, all right. And also for printed, because dry film photoresistant over there, for dry film photoresistant, and then for solar cell, and of course the last one is for hard disk platter, the surface of the hard disk. Okay, you can use SPS as well. Right. Now, in tribology, the study regarding to the interaction between metal and metal surface, the wear and tear. In mechanical FKMP, we have Pro Erwin, for example. He is expert in tribology study. I also involved in his research. We do SPS together on the tribology surface. Yeah? And one of my students also performed one of this study then. All right, in tribology, study on lubricant oil. How the lubricant can resist the wear and tear. So yes, we can use SPS as well. Right, some other applications I take from several books. Yeah? In metallurgy, grain boundary segregation, electronic structure, corrosion science, ceramic, ceramic catalyst, microelectronic, semiconductor, material, adhesive science, and so on. So these are some example of the from grain boundary. Yeah, this is an example how we can study on the grain boundary, and then we have the twin electronic structure of metal and alloy. For example, you got the pure metal and then compare with the alloy. So you see this, the spectrum is changed. Yeah. So this one we call as stoichiometric change. The chemical shift we call chemical shift. The peak position is changed from here to there, and then will be what? Will be increased. Yeah. According to the amount of the additive. Right. And then in civil engineering and so on. And we have the civil engineering as well. This is the typical SPS spectrum look like. So I think if you want to more detail, I think maybe afterward if we have the workshop later, we can join in Pago later on. Yeah, I hope so. So I stop here, but the thing is, a lot. Yeah. So I think they need 12 o'clock now. So, but last but not least, conclusion. This is the list of the high impact journal. Why surface science very important? If you manage to have a good manuscript, yeah, you have good data in SPS, you manage to submit your manuscript to high impact journal like surface science report, applied surface science, and then surface interface, progressive science, and etc. And my achievement, before I stop, I think let me share a bit on my achievement. Yeah, Alhamdulillah, last 1st of May, I have been awarded as the National Worker Icon, Alhamdulillah, received from our Prime Minister. And thank you to UTHM, thank you to my faculty of Science, And also thank you to Major Professor UTHM to bring me on the stage. Thank you. And then, and then, recently, in 2008, I received one, and now it looks like I received two high prestige award from husband and wife. Yes. The first award I received from Datuk Sri Wan Aziza in 2018. Yeah, I got two national award. Yeah, from two husband and wife. Our prestige leader. And then some of my contribution to UTHM, Anugerah Taat Setia, 20 years working, UTHM, Anugerah Khidmat Cemerlang, 10 years working in UTHM. Now I have nearly 25 years in UTHM now. Okay, and then this is my publication in Scopus right now, with nearly 17 Ash Index now. Alhamdulillah, the citation is more than 1,000 now. Yeah, even though not bad to me, scientists on on the wheelchair, what do you expect then? Okay, compared to normal scientists. Of course, I'm far away, but at least I try. Right, Prof. Insan, Prof. Azman? At least I try my best. Okay, and then my WS is nearly 16 now, Ash Index. Okay, and also, I'm also active in several, become as international peer reviewer for all this journal. So all these certificate I have got from the Elsevier, all are from Elsevier. Alloying compound, biochemical, and so on, material design, and so on. Yeah, all of this, right? And thank you to Major Professor. Thank you to my faculty of Science, Research, and also all the staff. Last but not least, to my lovely wife, Dr. Salawati Ahmad, my wife. Okay, she's there behind Prof. Rabia. Please stand up, please. Everybody can see you. Please, my wife, Dr. Salawati, she working at CLS, yeah. And also my family, my daughter, Adrina Zawani, Amdani Fatina, and also Ahmad Akmal. So by that, I end up my lecture and I pass to our chairperson. Thank you very much to all.
Ladies and gentlemen, abundant thanks to our honorable speaker, Professor Technology Dr. Zaidi bin Embong, for his lecture just now. Ladies and gentlemen, the floor is now open to the audience for the question and answer session. To all members of the floor, we are welcome to ask a few questions and kindly proceed to the mic provided. Any question from the audience? Yeah, there are one question from the Prof. Dr. Rabia, please.
Soalan saya rasa lebih kepada when I look at your slides, all your presentations, I'm thinking that this is very interesting and sampai saya rasa kesal tak belajar fizik betul-betul macam. Cuma kerisauan saya adalah when we too fundamental, even though we know that it is very important, apa yang you sampaikan adalah sangat-sangat penting, especially to industry. Saya rasa ada Siltera di sini. Cuma kerisauan kita adalah, well, I'm not wearing TNCPI topi, I'm wearing as Rabia Ahmad, yang saya melihat kepada masyarakat yang kini physics tu seolah-olah macam, lost interest. So how as an academic, as an educator, we want to bring physics, we want to bring interest to public to physics, especially when it comes to surface, interface yang saya kira macam tadi kan, kalau kita ambil simple example, you know, if you embed wrong materials to the body, what happen? And then when it comes to gas, yang kita kadang-kadang macam tadi Prof mention carbon, you know, and it's tested. Tapi untuk orang awam, right, orang yang di kampung-kampung, all that things sebenarnya perlu awareness, and awareness come from school. Tetapi interest to science subject and physics especially, dia semakin merundum. And as physics professor, I guess, what actually you want, if you can recommend to the public, especially to educator and lecturer, young academics for example, I mean to young academic and also for me, yang tak berapa nak muda ni, to bring back, you know, macam to come back. Ini macam hari ni saya tengok macam memang come back lah. Sampai saya kata macam wow, especially when it comes to X-ray dan sebagainya tu kan. So memang very important, extremely important to the world. Tetapi malangnya interest tu semakin mengurang. And tolak tepi lah whatever high impact journals. The most important thing, how it is applicable. So please Prof, thank you.
Soalan yang bagus. Saya jawab dalam bahasa Malaysia. Okay? Allow me to answer in Malay. Okay, lagi mudah faham Jadi kalau melihat, saya rasa idea masa saya bawa apa yang berlaku dekat UTHM contoh. Dulu masa penubuhan fakulti, masa Prof Zaki pun ada. Kita letak nama fakulti sains gunaan. Gunaan tu maknanya dia supaya apply. Sebab kita dalam M-Tun. Betul? M-Tun. Kalau contoh kita banding macam saya sendiri belajar kat UTM, Fakulti Sains. Contoh kalau macam UKM, FST kan. Memang kalau kita pergi sana memang kalau belajar tu mekanik kuantum tu pengiraan je semua tu. Kan betul? Saya pun sendiri kadang-kadang tertanya-tanya. Even saya seketika saya menjadi penemubual student calon-calon untuk my brain kebanyakan mereka nak pergi bidang aero angkasa, banyak benda kuantum-kuantum. Saya kata saya pun tanya soalan yang sama kan, dekat mana kegunaan dia. Jadi berbalik kepada apa yang saya sebut tadi, penubuhan fakulti sains Prof Zaki betul zaman tu kita discuss dengan Datuk Noh cadangkan letak sains gunaan. Saya nampak apa yang Datuk Noh letak tu, dia dah fikiran dia ke depan. Sebab kita ada gunaan. Gunaan maknanya bila pelajar masuk, dia tak ada belajar terus ke kata fundamental. Dia lebih kepada apply. Okey, itu kan. Itu apa yang berlaku dekat UTHM. Saya nampak. Supaya kita nak match dengan sahabat-sahabat kita yang lain di fakulti lain. Okey. Alright. Dalam konteks sekolah, kita tengok, kita tahu baru-baru ni banyak yang nyata dalam akhbar. Even menteri pun cakap, saya setuju, minat pelajar terhadap sains tu mula kakis. Okey, saya punya pandangan macam ni lah. Otak saya fikir macam ni. Terlalu banyak tengok YouTube, guna handphone. Prof Prof Rabia, ramai yang guna handphone. Walhal, saya nak tanya satu benda lah. Kalau tak ada handphone ni, daripada mana datang handphone? Konsep asas fizik, konsep asas sains. Jadi sains tak boleh dilupakan. Jadi saya nampak, untuk menambah minat pelajar, saya berfikirlah, kalau saya boleh bercakap dengan menteri lah, kan? Saya sarankan supaya kurikulum, silibus, subjek sains tu perlu menampakkan ke arah aplikasi. Jadi bila cerita pasal elektron, orang apa elektron apa? Okey. Benda yang visual yang tak boleh nampak boleh dinampakkan. Kan? Kalau contohnya Saya kata handphone ni, dalam handphone ni ada elektron. Agaknya minat tak? Sebab pelajar-pelajar sekarang ni, dia banyak dekat handphone tau. Okey, tengok teknologi lah, IT lah, IoT lah, apa benda bagai semua kan. Tetapi saya cakap tadi, semua teknologi berasaskan sains. Bagi saya, pandangan saya, sains adalah bahasa kejuruteraan. Tanpa sains, kejuruteraan tak wujud. Okey, kena setuju apa saya cakap. Alright, jadi saya rasa anak-anak di sekolah perlu didedahkan. Maknanya kalau silibus boleh dimudahkan. Nampak. Kalau dia belajar transistor tu, nampak benda tu. Itu satu. Kemudian kalau boleh, soalan tu janganlah sampai soalan yang jadi budak-budak takut. Ini tak ada. Saya cakap terang dekat dalam video ni saya cakap. Soalan kalau tengok cikgu yang bagi soalan, saya rasa kita yang duduk universiti pun dah pening. Tak, saya cakap terang. Jadi budak pelajar-pelajar, tanya anak saya Adlina tu, ada di belakang tu. Ramai kawan-kawan dia yang tak ambil. Sebab takut. Jadi bagi saya, Kementerian Pendidikan perlu ambil satu langkah yang mana sikap orang kata takut kepada sains tu dijauhkan. Maknanya dikurangkan. Tengok cikgu sains, takut. Tengok soalan lagi takut. Jadi itu sebab punca lah bagi saya hilang minat. Satu. Keduanya, peluang pekerjaan. Kadang-kadang bila ni mak ayah tanya kita, anak aku ni belajar fizik jadi apa? Rasa Prof Zaki pun tahu, betul kan? Dia mak ayah akan tanya, ni masuk ni jadi apa? Ni jadi apa? Betul tak? Jadi kita universiti terpaksa menerangkan. Okey, satu. Yang kedua, kalau tenaga dah ada, tapi peluang pekerjaan tak ada, macam mana? Betul tak? Maka bagi saya, pihak kerajaan perlu membuka peluang-peluang pekerjaan bagi pihak industri, perlu menerima pelajar-pelajar sains. Bukan sekadar menerima bidang engineering saja, tetapi bidang sains pun perlu. Saya rasa ada juga di kalangan pelajar-pelajar daripada FAS yang bekerja di industri, Prof Zaki betul ramai. Jadi saya nampak ini suatu benda yang agak sukar sebab melibatkan negara, melibatkan generasi akan datang. Kerisauan saya pula, saya tak takut satu ketika besok di Malaysia subjek fizik dah hilang. Itu kerisauan saya. Orang akan fikir engineering terus buat tu 4 dah dapat. Nampak? Cuma juga AI. AI bagus bagi saya. Satu masa besok otak manusia akan jadi museum. Sedangkan AI itu datang daripada otak manusia. Betul tak betul? Setuju tak dengan saya? Betul, saya tak kata tak nafikan. Tapi AI itu dia hanya memudahkan cara. Kan? Itu. Tapi yang buat tu otak manusia. Sama juga bidang kejuruteraan. Semua teknologi yang saya kata tadi, advanced material tu datang daripada ilmu sains. Kita sebab dalam fizik ada sains bahan. Kalau tak ada sains bahan, macam mana orang nak terangkan? Prof, sama juga saya kata tadi, method X-ray. Dari mana datang X-ray? X-ray tu datangnya saintis William Conrad-Roentgen. Conrad-Roentgen tu orang apa? Orang sains. Bila di era sekarang, kita di era industri, di era sekarang, oleh kerana teknologi pesat, itu namanya TVET. Kalau salah tu, saya tanya Prof balik lah. Saya tanya Prof balik. Dulu, nak masuk sekolah sains, gempak masuk sekolah sains. Siapa masuk sekolah vocational, budak yang tak terror. Betul tak betul? Sekarang, berlumba-lumba nak masuk sekolah vocational. Setuju tak dengan saya? Setuju. Pada era 90-an, saya rasa, saya minta maaf kalau sahabat-sahabat saya, Prof Nan, yang lain-lain, saya rasa ini adalah hakikatnya. Tahun 90-an, budak-budak yang masuk vocational, budak-budak yang result dia kurang. Sekarang, semua nak masuk vocational. Ini era dulu. Dulu sains agak dipandang. Okey, mengapa pengurangan berlaku? Disebabkan teknologi yang pesat. Ilmu sains, sedangkan ilmu sains ni adalah asas segala-galanya. Sama juga Al-Quran. Saya kata di Al-Quran. Sains datang daripada Al-Quran. Kita kena ingat Al-Quran tu. Dari mana puncanya? Semua datang dari sains. Kalau orang engineering nak marah saya tak ada masalah. Prof Nan kita boleh bincang belakang nanti. Prof Khairul ke siapa ada, Prof Hasan ke, kita boleh bincang belakang lah. Tapi bagi saya, tanpa sains, no teknologi. Itu sebab pelajar zaman dulu, dia kena masuk aerometrik, ambil sains dulu, barulah yang masuk engineering. Sekarang nak buat termodinamik tak faham, kalkulus tak faham. Betul? Sedangkan dalam contoh matematik, dalam bidang kejuruteraan guna kalkulus. Kalkulus pakai, DYDF pakai. Semua tu teknologi berasal dari situ. Ini sebab saya cakap, science is the language of the technology. Yes, technology come from Tibet. Saya setuju. Jadi soalannya sekarang, bagaimana kita MTON, UTHM yang berasalkan Tibet, kita nak membantu sains ni bantu Tibet. Itu yang saya rasa Prof Zaki tengah pening kepala dah. Dia dah pening dah. Kita dah bincang dah. Kita cuba ke arah itu. Untuk silibus tu samakan Tibet. Betul tak Dr. Afisha? Kita ada buat kan? Nak sains tu jadikan Tibet, Prof. Jadi soalan Prof bagus. Saya harap jawapan saya pun bagus. Saya harap pihak kalau sampai kepada pihak kerajaan Malaysia, saya minta maaf. Tapi ini bagi pandangan saya. Kalau salah, saya tak ada masalah. Okay? Terima kasih. Itu saja. Alright. Okay.
Alright, thank you to the Prof Zaidi and thank you to Professor Dr. Robi Ahmad, Deputy Vice Chancellor, Research Innovation for the questions. Ladies and gentlemen, we would also like to express our deepest gratitude to our speaker, the Honorable Professor Technology Dr. Zaidi bin Embong, for sharing his precious knowledge and expertise with us today. We are also taking this golden opportunity to congratulate the Honorable Professor Technology Dr. Zaidi bin Embong for his recent award of National Employee Figure 2024. May his outstanding achievement and his race inspire us to pave our own success history. Ladies and gentlemen, before we end the glorious event, we would like to invite the Honorable Professor Technology Dr. Hajar Roziati binti Ibrahim, Chairperson of Majer Professor University, as official representative of the UTHM Vice Chancellor, accompanied by the Honorable Associate Professor Dr. Muhammad Zaki bin Noh, to present a certificate and token of appreciation to Professor Technology Dr. Zaidi bin Embong, our invited speaker for today. Please welcome. Many thanks to Professor Technology Dr. Hajar Roziati binti Ibrahim, and also many thanks to Associate Professor Dr. Muhammad Zaki bin Noh. Ladies and gentlemen, every beginning had its end. So as this Majlis Syarahan Perdana 2024, I am Abdul Wafib Abdul Rahman, Master of Ceremony today. On behalf of the organizers, I would like to express a sincere gratitude to all of the being part of this event and looking forward to see all of you again by the near future. With that, I end with wabillahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh, and thank you. So we have a session photography session with the speakers at the stage. The Div, Honorable Div, and the invited guests.